Welcome dear learners. We are continuing quantum chemistry and in this module we are discussing Hartree-Fock self-consistent field HF-SCF method. The contents of this module are ab initio quantum chemistry methods, Hartree-Fock self-consistent field HF-SCF method for atoms, Slater determinants, Fock operator and SCF and variation method. First of all, ab initio quantum chemistry methods. Ab initio methods in computational chemistry are a category of quantum mechanical techniques used to compute the electronic structure of molecules and to predict their properties from first principles. These methods, these ab initio methods, are based on solving the Schrödinger equation for a system of interacting electrons and nuclei. That is, here also we are solving the Schrödinger wave equation of a system of interacting electrons and nuclei. Unlike empirical or semi-empirical methods which are very popular in quantum computational chemistry, the ab initio methods do not rely on experimental data or empirical parameters. These methods, these ab initio methods use fundamental physical principles to make predictions. Ab initio methods solve the time independent Schrödinger wave equation, that is Hamiltonian psi is equal to energy into psi, where H hat is an operator, well-known operator called Hamiltonian operator or total energy operator, and ab initio method solve the time independent Schrödinger equation. That equation describes the behavior of electrons and nuclei in a molecular system. We know the time independent Schrödinger wave equation, Hamiltonian psi is equal to energy into psi. Here H hat is the total energy operator, and in the ab initio method we are also solving this time independent Schrödinger wave equation for a system of interacting electrons as well as nuclei. Ab initio methods take into account electron-electron correlation, which is essential for accurate predictions of molecular properties. This correlation arises because electrons are indistinguishable and their movements are intertwined. We know electrons are fermions, they have a half integral spin, and these particles are totally indistinguishable, and hence the electron correlation is important as far as ab initio calculations are concerned. Ab initio methods use basis sets such as Gaussian basis functions to represent electron wave functions. These basis sets can be of varying size and quality. Hartree-Fock theory. The Hartree-Fock method is one of the simplest ab initio method, or this Hartree-Fock method or Hartree-Fock theory is a very simple ab initio technique or ab initio method, and this Hartree-Fock method provides a mean field approximation to the electron-electron interaction, treating electrons as if they move independently in an average field created by all other electrons. Consider we are having a system of n electrons, then that electron is under the field provided by other electrons, that is n minus 1 electrons. That is, the electron move independently in an average field created by all other electrons except the electron under consideration. Now, post-Hartree-Fock methods. To include electron correlation beyond the Hartree-Fock level, more advanced ab initio methods are employed. Such methods are known as the Post-Hartree-Fock methods. These Post-Hartree-Fock methods include configuration interaction CI, coupled cluster CC, and density functional theory DFT. CCSD or coupled cluster single and doubles, and MB2, that is molar placet perturbation theory, are common post-Hartree-Fock methods. Density functional theory. Density functional theory, abbreviated as DFT, is a widely used ab initio method that approximates the electron density rather than the wave functions. That is, the density functional theory gives emphasis to electron density other than the individual wave functions. The density functional theory provides a good balance between accuracy and computational efficiency, making it suitable for studying large systems. That is, it is possible to study many electron systems with the help of density functional theory. Molecular properties. Ab initio methods can be used to calculate various molecular properties such as electronic energies, molecular geometries, vibrational frequencies, electron spectra, and reaction mechanisms. Accuracy and computational cost is very relevant as far as the ab initio methods are concerned. Ab initio methods vary in their accuracy and computational cost. High-level methods like CCSDT or coupled cluster singles, doubles, and perturbative triples are more accurate methods, but these methods are computationally expensive. However, methods like density functional theory is less accurate and computationally efficient. So, the methods may vary and the accuracy may vary and the computational cost may also vary. Now, we are going to focus on the present day title, that is Hartree-Fock self-consistent field method or HF-SCF method for atoms. Before entering into the details of this Hartree-Fock self-consistent field method, HF-SCF method, we have to first focus on the Hartree's method. After that, we are gradually entering into Hartree-Fock self-consistent field method. So, as an introductory remark, we have to consider Hartree method first, followed by the HF-SCF method. The Hartree-Fock self-consistent field HF-SCF method is a fundamental approach in quantum chemistry which is used to approximate the electronic structure of atoms and molecules. The HF-SCF method, the Hartree-Fock self-consistent field method, is named after two scientists, two physicists, Douglas Hartree and Vladimir Fock. They made a significant contribution to its development. That is, they together developed the Hartree-Fock self-consistent field method. The HF-SCF method is a key component in broader field of quantum chemistry which seeks to understand and predict the behavior of electrons in atoms and molecules. The approximation methods like variation principle, perturbation theory, etc. does not give very accurate result for the solution to Schrodinger wave equation for helium atom, which is a simple 2-electron system. It should be noted that in the case of many electron systems, it is not easy to solve the Schrodinger wave equation. In that circumstance, we have utilized certain approximation methods. The two prominent approximation methods in quantum chemistry are variation principle and perturbation theory. However, these approximation methods will not give very accurate result for at least helium atom problem, which is a 2-electron system. Hence, we require more and more best approximation methods. And at this point, the Hartree-Fock self-consistent field method is highly relevant. For other atoms in the periodic table, the number of interelectronic repulsion terms in the Hamiltonian will increase, thereby rendering the exact solution of the wave equation even more difficult. This implies that it is too tough to solve the Schrödinger wave equation for many electron atoms from the periodic table. This is because of large number of interelectron repulsion terms that may appear in the Hamiltonian of the concerned systems. Hence, to get the easy solution for Schrödinger wave equation is a very difficult task. Thus, we need more powerful methods for calculation of ground state energy and wave functions of many electron systems or ions. In this circumstance, in 1928, the British physicist D.R. Hartree suggested that the wave function of an n-electron atom be written as a product of n one-electron wave functions. This is very important assumption, and this is the very basic principle behind Hartree method. That is, the wave function of an n-electron atom may be represented as a product of n one-electron wave functions. This statement can be mathematically represented like this. Here we are having a quantum mechanical system, an atom of n electron, or a system consists of n electron. The total wave function is psi of 1, 2, 3, etc. up to n. This is total n electron wave function, and that total n electron wave function can be represented as a product of n 1-electron wave functions. That is psi of 1, 2, 3, etc. up to n equal to phi 1, 1, phi 2, 2, phi 3, 3, etc. up to phi n, n. And all these are 1-electron wave functions. This is n-electron wave function. Here it is clear that phi I are normalized and mutually orthogonal 1-electron wave functions. Now, what is meant by normalization? The two 1-electron wave functions are mutually orthogonal also. Normalization implies each function satisfies the mathematical condition integral phi I star phi I d tau is equal to 1. Condition for normalization is this one, and the condition for orthogonality is integral phi I star phi j d tau is equal to 0. That is, two individual 1-electron wave functions are mutually orthogonal and as such normalized, where phi I are normalized and mutually orthogonal 1-electron wave functions. Thus, phi 1, 1 means that electron 1 occupies atomic orbital phi 1. Phi 2, 2 means that electron 2 occupies atomic orbital phi 2, and phi n, n indicates that electron n occupies, or nth electron occupies atomic orbital phi n. Thus, total n-electron wave function can be represented as a product of n 1-electron wave functions. Hartree proposed that the self-consistent field, or SCF method, according to which each electron is assumed to move in a spherically symmetrical potential due to the nucleus and the average potential of all electrons except the one under consideration. Thus, the potential energy in arbitrary units of electron 1 can be written mathematically as V1, V1 stands for potential energy of the first electron, that is equal to minus Z divided by R1 plus sigma I not equal to 1 integral phi I square I divided by R1I d2I. Similarly, for every other electron I in the atom, we can represent Vi is equal to minus Z by Ri plus summation J not equal to I integral phi J square J Rij d tau J, where the first term in these expressions is the attractive potential energy between ith electron and the nucleus. Since this force is force of attraction, it is definitely a negative term. The second term in equation 3, represents the self-consistent field, and here Rij is the distance between two electrons I and J. Using equation 3 for Vi, the Schrodinger wave equation for ith electron in an atom can be represented as minus half del I square plus Vi of phi I equal to epsilon I phi I, where I is equal to 1, 2, 3, etc. up to n. Here, epsilon I is the energy of the ith orbital phi I. The n nonlinear simultaneous equations cannot be solved since Vi requires a prior knowledge of all other one electron wave functions phi j. The SCF method or self-consistent field method is as follows. First of all, we have to choose an arbitrary set of atomic orbitals like phi j, phi k, etc. The potential energy field Vi arising from all the electrons except ith electron is calculated from this chosen set of wave functions, and equation 4 is solved numerically on the computer to obtain phi I. The procedure is repeated for each of the n electrons present in the atom. If phi 1 1 star dash, phi 2 2 dash, phi 3 3 dash, etc. are self-consistent orbitals, then total wave function for n electron system is given by this expression psi dash 1 2 3 etc. up to n equal to phi 1 dash 1, phi 2 dash 2, phi 3 dash 3 etc. up to phi n dash n. The corresponding energy is given by these expressions integral psi dash star h hat psi d tau. On simplification, we are getting so many expressions, and omitting further mathematical details, we can arrive at a final mathematical result for energy epsilon. Energy epsilon can be calculated by SCF method using this expression. In 1930, the Russian physicist Vladimir Fock proposed that since the Hartree-Fock wave function was the product of n one electron spatial functions, an improved wave function should include both the spatial part and the electron spin part. In SCF method proposed by Hartree, they consider only the spatial part of the electron, and Fock later by Slater suggested that for a complete wave function, it must contain two components, the spatial part and the spin part of the electron. This suggestion had also been made by J.C. Slater. Fock solved many electron Schrodinger wave equation using such a wave function and the Hartree method. This technique, by incorporating spatial component and spin component of the electron wave function, we are getting the new technique, and that technique is called Hartree-Fock self-consistent field method. Now, spatial orbitals and spin orbitals. We know an orbital is the region of space where the probability of finding an electron is maximum, or an orbital is defined by the wave function of a single electron. The spatial distribution of electrons in a molecule can be described by spatial orbital psi of r vector. However, a spatial orbital is not sufficient to completely describe an electron, since it is necessary to specify its spin function. It is possible to define a function which describes simultaneously the spin and the spatial distribution of the particles. Such a function is called a spin orbital. That is, a spin orbital describes the spin part and the spatial distribution of electron simultaneously. Now we are discussing the Slater determinants. The Pauli's exclusion principle states that in a system of indistinguishable fermions should be described by a antisymmetric total wave function. That is, psi total is the product of two parts: the symmetric spatial function psi space and antisymmetric spin function, that is psi spin, or simply psi total equal to psi space into psi spin. Thus, for helium atom, which has a ground state configuration of 1s2, there are two electrons. The spatial part of the wave function psi space can be represented as 1s1 into 1s2. The interchanging of these two electrons leads to the wave function psi space equal to 1s2, 1s1. That is, the psi space, the spatial part of the wave function, is symmetric, hence abbreviated as S. However, if we consider alpha and beta, which represents clockwise and anti-clockwise spin of electron, then we can write psi spin as psi spin equal to alpha 1 alpha 2, which is symmetric, 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1, which is again symmetric, 1 by 2 alpha 1 beta 2 minus alpha 2 beta 1, which is antisymmetric, and beta 1 beta 2, which is symmetric. These are spin components. Thus, we can arrive at psi total equal to psi 1 2 equal to 1s1 1s2 into 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, which is again equal to 1 by root 2 into 1s1 alpha 1 1s2 beta 2 minus 1s1 beta 1 1s2 alpha 2. This expression can be written as a 2 by 2 secular determinant, and that secular determinant is of the form psi 1 2 is equal to 1 by root 2 factorial multiplied by the determinant 1s1 alpha 1 1s2 alpha 2 1s1 beta 1 1s2 beta 2, and this is called the Slater determinant for a 2 electron system. Similarly, we can construct the Slater determinant for many electron systems. Now, the last part of the discussion, that is the Fock operator. The Fock operator, abbreviated as F hat, is an operator in quantum mechanics that operates on a 1 electron wave function or orbital and is employed to build the Hartree-Fock wave function. That is, F hat operates on 1 electron wave function. The Fock operator F hat obeys the eigenvalue equation F hat psi I is equal to epsilon I psi I. Here psi I represents a 1 electron wave function, typically an orbital, and epsilon I represents the energy eigenvalue associated with the orbital psi I. The Fock operator F hat is constructed by summing the kinetic energy operator, the electron nucleus attraction operator, and the exchange operator while subtracting the electron-electron repulsion operator. SCF and variation method. The key differences between SCF and variation methods are described here for convenience. The variation method is a general mathematical technique used to approximate the solutions to quantum mechanical problems, whereas the SCF method is a specific application of the variation method tailored for electronic structure calculations in molecules. In the variation method, the trial wave function is adjusted to minimize the energy and obtain upper bounds to the true energy. In self-consistent field method, the primary goal is to achieve self-consistency in the wave function by iteratively optimizing the one electron orbitals until a minimum energy is achieved. That all about the discussion on HF-SCF method. Have a nice learning experience. Thank you.